So for those of you all that are here in person as well as those that are online, I got a couple of interesting comments, questions on Twitter that I want to bring to the group. So the first comment was effectively a function of, Drew was talking about matrices and data frames. And if you go look on Twitter, there's some folks that talk about creating a matrix and coercing it into a data frame. Of course, data frames do take a lot more memory. And so as a consequence, that's something to be considerate of. But a matrix can only store one type of data at a time, so that's your trade-off. So the question then, that's kind of some of the discussion, but the question that comes out of that is, it says, Drew mentioned that vectorizing, this is from Sean Hoban, Drew mentioned that vectorizing can eat up memory. At what scale is that a problem, and when should you not vectorize? So I'll turn it over to Drew. Thanks.
So that's a really great question, and it gets to something that I haven't explicitly stated but have been sort of trying to slowly build a case for, and will explicitly state at the very end. The idea that when I say something is expensive, expense is relative, right? If you're Bill Gates, maybe expensive for you is not the same as expensive for little old me. So when I say vectorization consumes a lot of memory, what I mean is, like on the last example here, right? We see that I'm forming an intermediary vector of 1 to n, right? So I don't have to do that if I have access to, for example, compiled code, which we'll show you in a moment, where I can just take the input and then square the values and be done, right? When would that memory use be an issue for you? Depends on your needs. Sometimes vectorization, people get really, really crafty with vectorization and end up making copies of like matrices. That might be at a point where you need to drop to compiled code. It just really depends on your performance and your needs. So the very simple answer I would give is profile. Determine whether or not it really is an issue for you. If it's not, if it's not broke, right, don't fix it. But if it's slow, if it's consuming a lot of memory, then consider a rewrite in some other kind of expression or some other format, right? So let's.
Actually, I have one other really small question. Sorry. I have a question on Twitter that says, I can't get rprof to work in my R script being called using R script. Is there a trick to it?
When you use rprof in batch, I don't think so. I don't remember. That's an interesting question. I don't remember there being an issue calling it in batch. I will have to check, so I don't remember.
Okay.
Hopefully somebody on Twitter could answer that. It might tell you, like if you do $rprof, that'll load the help or help rprof. It may tell you in there. I just don't remember off the top of my head, unfortunately. It may have something to do with like where temporary files are going. I'm really not sure at the moment. Okay, so this is maybe the most important part of the tutorial, in my opinion, interfacing to compiled code. Why is it important? Because the effects are dramatic, and it's really not that hard. It's really not that hard to do these days. A few years ago, it was, in my opinion, much harder, even using the tool that I'm going to be describing, RCPP. These days, it's really, really easy to start utilizing compiled code. So I have a lot of things to talk about in this section. Hopefully, we'll get through them all in a reasonable amount of time, give you some time for exercises. First, we're going to have an introduction to RCPP, foreign language interfaces, what is it, why would we want it, documentation, and help. So I wrote this years ago. You could update it. It wasn't very complicated. But the point is, R is mostly a C program. So if you look at the lines of code of core R, by percentage, C is dominating. There's a lot of Fortran. There's slightly less R, but it's overwhelmingly a C program. So therefore, the things that you can link with C, things that interoperate with C, can interoperate with R. That's literally everything. So anything you want, you can bring to R through C. This is contributed packages. So from the CRAN, this picture would probably look very different today. This is a few years old. But you could make your own mirror of the CRAN and check for yourself. This thing is driving me crazy. Hang on. I think my adapter is maybe going bad on me. Oh, please stop. Yeah, I might, if you have one. I'm going to try one more time, and then I may take you up on that. I'm pretty sure it's my adapter. All right, well, fingers crossed. Hopefully, I could do it blank, and you could just follow along on your laptop. Is that? I may. Let's see if it dies again. Thank you so much, though. Okay, so if you look at packages on the CRAN, they are, something weird always goes wrong in these things. So if it's only that, then we're very lucky. So overwhelmingly, people are writing R code when they're contributing packages to the CRAN, then C, then C++, then Fortran. Again, probably that picture would be a little different today, but I suspect R would still be dominating. There are a couple of interfaces to C and C++. There's .call, which we will sort of implicitly be talking about. There's .c, which is deprecated, don't use it. Fortran, if you can access your Fortran through C, and that's not very hard to do, then you can access Fortran. .fortran exists, but I don't suggest you use it. There's an R Java package, an R Python package for calling Java and Python. There's probably other things. But we're basically going to focus on C++ via RCPP. We're going to focus on compiled code as opposed to just all possible foreign languages for R. What is RCPP? Okay, it is a prettied interface, a set of utilities that make it easier to write compiled code and bring it into R. Okay. It's also a package ecosystem. There's all kinds of RCPPs now. There's RCPP Armadillo, which is for like linear algebra. RCPP Eigen, which is also for linear algebra. There's what's that library? RCPP GSL, GNU Scientific Library. There's all kinds of RCPP packages that make it very easy to bring existing libraries. There's, I think, even a thing for Boost now if you really hate yourself and want to use Boost. So again, it's utilities to make writing C++ more convenient for R users. The thing I'm going to emphasize several times, it's a tool which requires knowledge of C++ to effectively utilize. Okay? It makes that process much, 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 much simpler than it would be without RCPP, but there are still just some things that you'll need to pick up along the way, right? You can dive in on day one and make some dramatic impacts, but eventually you're going to hit a wall where you need to understand that C++ is, it's a low-level language, even though it pretends it isn't sometimes. It's a low-level language, and you may need to learn some things about like pointers and the way memory allocation works in C++, and memory leaks and things like that. So it's not completely free, but it's about as close as you could possibly get. It's pretty nice. It's GPL licensed, just like R. I just bring that up because people sometimes ask. So it's not magic, but it's close, right? The other thing I'll emphasize, it is not an automatic R to C++ converter, okay? It is something that makes writing C++ and integrating it into R very easy, but it is not an automatic R to C++ converter. It's also not as easy to use as R. It's really great. I don't want to diminish that, but it's not as simple as just using plain old R. Why would you care about RCPP, compiled code? It's crazy fast. It's really nice. RCPP is really easy to install, has a ton of documentation. It's becoming a standard in the R community for a way to integrate C++ code into R. It's actually even better documented than the basic C interface for R, believe it or not. It has a very large, friendly, helpful community, and if you really want to get help, just say like this is bad, I don't like it. And Dirk himself, the author, will find you and he will tell you exactly how to do it correctly. So it's Dirk Edelbatel. He's a great guy, but he's an outstanding guy. I agree. But I've seen him vigorously correct some folks before. Let us say. No, but he's an absolutely outstanding guy. So this is a little plot that I made again a few years ago. It would probably be even more impressive now. These are packages on the CRAN that are utilizing RCPP in various ways. I forget what the blue and red are. One is maybe a linking to, and one is depends or something, or depend or suggest. I don't remember exactly, but a ton of packages. It's actually even, I think it's maybe doubled since I made this plot. I just couldn't find the code to remake it. So lots of people are using it, right? It's a really great tool. What are the disadvantages? Well, it's C++, right? And C++, there be dragons. C++, difficult to debug and profile, especially because RCPP is a template library. So profiling kind of goes out the window a little bit. It becomes very, very difficult to figure out where something is slow and why. But if you're going from R to C++, you won't notice. Like, it'll be so much faster anyway. You can worry about that later. And it's designed to only work with R. So if you're writing new code and you're not wrapping it with RCPP, you can't ever easily repurpose it. This has changed dramatically since they introduced attributes. We'll talk a little bit about that, where this is almost not even true anymore if you're a little judicious about how you write things. But code reuse may be a slight issue, is maybe a better way to say that. So documentation and help. There are numerous vignettes for RCPP. Several of them are slightly out of date. But the introduction, quick ref, and FAQ are very, very, very useful. So Hadley has this thing, high performance functions with RCPP. You can read. It's pretty good. Dirk actually has a book, Seamless R and C++ Integration. It's a Springer book. So if you're at the University of Tennessee anyway, you can get that through the library, a PDF through the library for free. I've looked through it. It looks pretty good. I haven't read it, so I can't make a real recommendation, but it looks good to me. So, and I'm picky, so that's a pretty strong recommendation, as people who know me can probably tell you. Where to get help? The documentation is great, as I say. The RCPP tag on Stack Overflow is very useful. There is an RCPP Devel mailing list, which is also very useful. Twitter, again, is very useful. Some basic suggestions. If you're new to C++, I would say you probably need a book on C++ too, if you get really serious about integrating compiled code into R. I would say be patient. C++ is a really bizarre, complicated, hard, confusing language, but it has a lot of power and benefit to learning it. And then I say learn the art of reading template explosions. So when you make an error in C++, there's this joke that C++ is the only language whose errors are longer than the programs. And it's not even a joke, it's true. So learning how to read C++ errors is an art form, in my opinion. And it can be kind of overwhelming where you have like a 10-line function, you go to compile it, and you have 1,000 lines of errors. You feel like, what on earth have I done? It's really not so bad. Just start from the top and sort of look through until something stands out to you. But I've seen firsthand people be turned away by this kind of thing. So I just want to set the tone. This really isn't that bad, but you should be aware of some things. If you know R, never use dot in object names. We can't do that in C++. You should end your lines with a semicolon. Returns of functions need to be explicitly named. If you don't, at least in C, that's undefined behavior. I assume it's the same as C++. Every function in R has a return. In C++, if you know C++, we don't have voids. Side effects and functions basically don't exist. There's a caveat to that, not worth getting into. If data is modified, you should do it in a copy. Back to that issue of side effects. R functions are not thread safe. So garbage collection, so memory allocation, the random number generator, these are not thread safe. That's important to know. You can use multi-threading with these things. I think in the section 4 exercises, there's an example of using OpenMP with RCPP in the parallelism section. So it can be done. You just have to be a little careful. Make sure R doesn't get called anywhere. Okay, so using RCPP. So as I said, there's a C interface, which really RCPP is making much more palatable, much easier to use. So there are sort of these two faces of bringing in C and C++ code. You can use the C interface, or RCPP, which again has RCPP Armadillo, GSL, there's Redis, CNPy, which is stuff from NumPy, I think, RCPP Eigen. Also, there are RCPP 11, which uses C++ 11 stuff internally, RCPP 14, which uses the C++ 14 standard internally. All kinds of stuff. They're very busy, very productive folks. And they make great stuff. What's the difference between these two, though? How can I convince you that RCPP is really great, especially if you're a beginner? Let's construct this list object. Okay? So it's going to be a list, and it's going to have, the objects are going to be named. The first object is named A, and its element is 1L. L, of course, for integer. Then the other object is B. So B will be 2.0. That'll be double precision. Let's create this with first the C interface, no RCPP, and then with RCPP. Here's how you do it in C. Do you know what it does? Isn't it obvious? Right? It's complicated. So here we allocate the objects A and B. We set the objects A and B. We allocate the return vector. We allocate the names vector for the return vector, or list if you like. It's of type vec_SXP, which is even more confusing. Then we set the attributes, our name symbol of the names to the list. We say unprotect 4. Why 4? Because we protected 4 things. You have to count them yourself. And then say 4, and if you give the wrong number there, crazy things happen. And then you return. So that's how the C version works. Here's RCPP. So here instead, we just have to deal with the fact that we have these different types. There's RCPP integer vector. This is the analog of this fellow here. Because remember, we don't have scalars. We have vectors of length 1. So I'm constructing a vector internally in C, I'll call it, or C++, I'll call it A, has length 1. And it's an integer vector. I also have a numeric vector. In C++, we'll call it B. It'll have 1 element. I set them. C++ is 0 indexed. So in R, you might say A1, or even just A. But here we have to be, what I'm about to say, I have to be careful how I say what I'm about to say. So instead, let me just say that you might say A1 in R, and you might say B1 instead of this in R. So how do we create a list? We say RCPP list, and then we name the object. So we're declaring the type ret. It's RCPP list. And then we say list create, and it's going to have named element A, named element B. It's different from R, but would you rather have that? Right? I mean, this is really gross, right? So this is much better. Now, I cannot in good conscience describe C++ as something that's like easy or good for beginners, but if you're going to interface to compiled code, this really is about the easiest you could possibly make it. It's not as scary as I've sort of prefaced. I just want to set the tone that, you know, it's not automatic, it's not free, but it's really nice. It's very clean, and if you like C++, you're going to fall in love with RCPP. It's very, very C++y. So using RCPP with R, we are going to describe a way that you probably shouldn't do in production, but is really great for things like prototyping, things like instruction. We're going to use, so the question is, C++ is a compiled language. You want to compile, link, load, wrap, all of this stuff. This is a bunch of complicated stuff. I don't want to introduce these concepts. So I'm going to use this thing called source CPP, which is a utility provided by RCPP. And it will do all of this for us in basically one simple call. It's really great for prototyping. It's really great for teaching instruction. If you have something more long-term, you should investigate maybe writing an R package. That goes well beyond the scope of this discussion. I just want to bring that to your attention. So what we will do is, in R, we'll make a string, a character string, containing our C++ code. We use source CPP on that string, and it's going to compile, link, wrap, load. It's going to do everything for us. And then we can call the function by the name, by the C++ name that we gave. It's really cool. So how does it work? Here's an example. If I say code is, and now I'm starting a string, we include RCPP. This RCPP export, it comes from RCPP attributes. I don't want to maybe spend a lot of time on it, but if you're curious what that does, you can look it up. If you're familiar with C++, you probably could guess what it does. So I'm going to say int. Well, that's not an R type. SEXP is an R type. Every object in R is called SEXP in C, right? So when I say int, why am I allowed to do that? Well, RCPP is very clever. And this export business is actually going to take this and wrap it up into something usable by R, even though we're not being explicit with the types like SEXP or integer vector, numeric vector, and so on. It's very slick. It's very clever. I can't overemphasize how nice this really is. So we're going to define this function +2. Okay? It's going to have an integer return. It's going to have an integer input. What is it going to do you think? It's going to take that input, it's going to add 2 and return it, right? And then we end the string. So this is R code, okay? I mean, really, this is C++ code, but we're thinking of this being in R, okay? Whoops. So then I say library RCPP. Source CPP code is equal to code, this object here, this string. And now I can call the C++ function by its name in R. +2, 1, returns 3. Really, really, really slick. Really nice. This is so much easier than it has been historically to work with compiled code. So it's pretty great. So questions before we start hitting examples? Okay. So we're going to do the numerical hello world, which is the Monte Carlo simulation for pi, right? How does that work? You imagine, sampling from the unit square, things above the unit, so the first quadrant of the unit square, things above the unit circle, or outside the circle, things inside. This allows us to estimate pi basically by this. The reason why that estimates pi is surprisingly interesting. It has to do with almost sure convergence. It has nothing to do with area, as some people claim. Anyway, it's just a cute fact. We're going to do this in R using loops. We're going to do this in R using vectorization. And then we're going to do it with C++ using RCPP. And then benchmark, examine the performance. So here's how you might do this in R. Using a loop. Here we go. So we're defining a function mcsim_r. It's going to take input in, defining how many of these samples we want to have. So we initialize this value to 0. We take a random uniform value, another random uniform value. If the sum of those squares is less equal 1, we update the count and then return 4 times the count divided by the total. Very simple, right? Has anybody not seen this example in some fashion in some language before? This is the numerical hello world. So almost everybody, if you haven't, don't feel bad, but it's overused, and for that it's useful in learning new things, I guess. Here's how you might do it with vectorization. So instead, we're going to generate all of our data up front. So 2n random uniform values, right? So here we see we're overusing the amount of memory that we really need, right? It's using a lot more memory than this. Okay, so then we put that in a matrix, square the values, take the row sums, and see which of those are less than 1. So here we create more than we need, right? This matrix may actually even make a copy as well. This square will make another copy, sort of another vector if you like. Row sums will make another. This will create a Boolean, or a logical rather, a logical vector creating another vector, and then sum it is a single value. So lots of memory allocation going on, back to that original question. and then we return 4 times the count divided by n, right? And here's how you might do it in C++. It's slightly more verbose because I have to declare my type, right? Type is not implicit, although now there's this auto construct in C++ 14. But for the moment, you have to be very explicit about your type, right? So, drop this, and this should look pretty similar to the for loop version that we did, right? That first version. If we drop back here, if you have that picture in your mind, and we go here, it's basically the same. What's changed is basically this function call and the way loops look, for loops look. It's basically the same, right? And then, again, library RCPP. We source CPP, code equals code. And now the function mcsim_RCPP is callable from R. Pretty nice. So we benchmark them. N is 100,000. So we take the loop, the vectorization version, and then, oops, I used to have a C version in here. It turned out to be too much to talk about. I posted a discussion of that on my blog. You could see that if you care. It's pretty low level. So ignore that. That's not there anymore. It's too much to talk about. So then we can look at the RCPP version. And what do we see? The relative performance of the for loop version is really crummy, right? Really crummy. Loops are bad. If we vectorize, we get much better performance. And if we drop to compiled code, we get another pretty strong performance improvement. Now, a lot of examples you look at, and there's one in the exercises where there's something like a 34,000-fold speed improvement. Actually, 34,000. It's a bit of a joke, but I encourage you to look at it. We only got a 6.4 fold improvement dropping to compiled code. Why might that be? The reason basically is because hitting the random number generator, hitting the random number generator is a lot of the work going on here, and that vectorized function is actually pretty darn good. We're still able to beat it pretty handily. Why? Because of all those memory allocations that were going on that we didn't need in the compiled version. So how much performance improvement should you expect to get going to compiled code on average? People quote all kinds of numbers, right? Compared to like a really good implementation, just thinking about runtime speed, right? There's other considerations, memory use. But just thinking about runtime speed, some people say tenfold. I think 40 to 50 is probably a good sweet spot. In the wild, I have gotten more than 10,000-fold improvement on real problems. So it depends on what you've been given and how much time you can spend on it making it fast and how slow it was to begin with. We can really see the spread and the effect of the problem size if we scale this out a little bit and instead only look at the vectorized and RCPP versions, because the for loop would take way too long. I don't want to run it at that scale. And we see the relative performance of the C++ version has dropped slightly. That doesn't surprise me terribly. But it's still much better because we're avoiding all of those extra unneeded memory operations, among other things, actually. So what about the compiler, right? What about the bytecode compiler? Well, that changed the picture dramatically. So I compile all of them, and did it change? Well, the elapsed times are very different. The relative times are only really slightly different, right? The compiled version is still doing much better. The bytecode compiler did help, but we're still able to beat this with RCPP. Computer scientists are already angrily formulating an email to me about this slide. But so this is like in giant air quotes, okay? If you go back and you count the number of integers and doubles that you're using in each of those functions, I mean, it could actually, this is sort of like a lower bound, let's put it that way. Or a better way to say this for our computer science friends is this is O of n in terms of memory performance, this is O of n, and this is O of 1. So if you don't like that terminology, I would just simply say the amount of stuff that you need to allocate here depends on n. Here it depends on n, and here it does not. Right? So the memory usage was much better in the compiled version. That may matter to you. For a very large problem, thinking about operating on matrices, copies of matrices are much more expensive than copies of vectors, generally, right? Here in this version, we're just making some new vectors. If we were copying matrices, that's incredibly expensive potentially, or data frames would be even nastier. Then all of a sudden, this picture looks even worse. So a lot of people only want to talk about speed. Memory is important too. The two are sometimes related, but you don't want to start swapping out to your disk when you get to a really large problem, because then your speed really will be terrible. So a quick summary. This is just a quick table summary, and if you care about trying to replicate the numbers that I have here, I basically tell you how you could. This is my environment, processor, R version, compilers, compiler flags, and all that stuff. Probably don't care. It's a simple enough problem anyway. So, for example, I would expect the memory usage for the loop version to be, a couple megs, maybe 10 times that, and then almost nothing, right, to really hit the point home for that value of n equal 100,000. Okay? Questions so far? So that's a really simple problem, right? If your problems in real life are that simple, life is wonderful. So in that case, you may look at this and go, well, vectorization's fine, right? The performance of vectorization is fine for my needs. But again, this is just an example problem. It's simple to digest. It's a typical example. You may have seen it before. For real problems, I would expect the performance for compiled code to actually be better on average. The more complicated it is, R is so aggressive with memory allocations. And so the more crafty and clever you are with vectorization, the more of those you're doing, whether you realize it or not. And so dropping to compiled code allows you to just avoid that completely. So anyway, I hope that point is clear. I don't want anybody walking away thinking, why even bother? Because really, there's a lot of reasons to bother. Some thoughts. Bad R code often looks like good C++ code. Did you notice that? If we hop all the way back, I know I'm hopping slides a lot, and I hate it when people do that, but bear with me. If you look, this looks a lot like the C++ version, right? So, and that was bad R code. We agree, right? We agree that that's really bad. Do we agree that 200 times worse is bad, right? So bad R code often looks like good C++ code. So thinking about how you want to solve your performance issues in R can be tricky. You might think, do I want to try an sapply or an lapply or an mclapply, which we'll talk about next session? Would one of those be beneficial for me? Or would it really be better to think more in an imperative language like C++ and an imperative language pretending to be functional these days, like C++, and think on that paradigm? It sort of depends on what your problem is. Is it really that slow? You'll always, if you're really judicious, be able to get better performance here, but it may be difficult. Unless somebody's already done it, right? If somebody has a single function that solves your problem, use it. Don't reinvent the wheel unless you're really confident you can make a better wheel. R's memory footprint is terrible, right? We saw all those different vectors that are being implicitly created and thrown away. And if your problem is very large, or if that had been like a really large simulation, then those performance effects would have compounded. Okay, so we have another example. This is a real example from the wild, and I like it a lot. It's cosine similarity matrices. So a little bit of background. From vector calculus, you can define the cosine of these vectors x and y. Think about just like Rn vectors or R3, whatever. You can define like so. And so the cosine similarity we can define like this. Okay, so we want to take the dot product divided by the norms of the vectors. So this is the cosim, right? If we want to form the cosim matrix, we do this for all pairs, basically, is the idea. This is not new to you, probably. Why would you care about it? It's useful in certain kinds of like text mining scenarios. I forget exactly. Somebody emailed me a question about this, basically, and it's why I find it very interesting. In CRAN, there's a package called LSA. As of version 0.73, if you look in the folder r lsa.r, you will find this source code. Okay, so I didn't write this. This is not mine. I want to make that very clear. Not because it's bad, just because I think it's important to give attribution, right? Although there are a few things in terms of performance that I don't like about this. Can anybody spot them very quickly? Well, there's one thing that I haven't talked about that's kind of nasty, and it's true in all languages. It's especially true in R. Name of the function. What are we doing? What are we doing? It's recursive, right? And that's bad in terms of performance. And people like to point out that, oh, recursion's fine in a compiled language because your compiler will fix it. R will not. So recursion in R is kind of nasty. So there are performance issues here. There's also a lot of data movement and creation and destruction that's really unnecessary. You can avoid a lot of this by actually even simplifying the function. Believe it or not, this is faster. I'll prove it. But instead, right, there's sort of a lot to take in here, but somewhere in here he takes a cross product. Yeah, okay. So he takes cross product divided by square root of cross product x times cross product y, after he's sort of reduced this thing recursively. In fact, if just right up front you take the cross product and then think about the diagonal of the cross product, you can simplify that exact function in this way. And it's maybe a little deeper than it's worth spending time trying to digest. Just take it for my word, this is the same thing. And there's a few more operations where here I'm only operating on one triangle, so then we need to make it symmetric. Pretty standard matrix stuff. If you don't work with matrices a lot, this may be a whole lot to digest, but it's still a useful example. Because now we're going to look at the C++ version. And again, ignore all this stuff up here for a second. If you just think about here, right, operating on these elements, we're only lightly expanding. It sort of doesn't look like it because we have to hop slides, unfortunately. We're really only lightly expanding this work when we drop to compiled code here. So I'm going to be very explicit now. RCPP numeric matrix. Okay, so this is a we need to declare the return of this function. This is the return type. So we're going to send back a matrix of doubles, basically. The function is fill loop, this piece here. Fill loop, numeric matrix on, we're passing in the cross product as a matrix. We're passing in the vector of the diagonal. And we're going to be doing some updates, basically. We'll set the diagonal of the output, the cosim, to 1, and then otherwise we use this, basically this line of thinking here, down here, and that's basically what we're going to do. We're only exporting a piece of the work because I'm still going to take the cross product in R. Why wouldn't I? I'll still take the diagonal in R. Why wouldn't I? If you drop it down to C++, there's almost no difference, I checked. And then you can just call the fill loop, and then you're done. Okay? So there's There's maybe a little more to digest here if you're not comfortable with matrix operations, but, and if it hadn't split there, I actually didn't even notice. It's a more powerful illustration. But if we benchmark them, so 10 replications, because this is kind of expensive, what we're going to do is check on a 100 by 100, a 200 by 200, a 300 by 300, all the way to 1,000 by 1,000 matrix, and benchmark the original implementation from the R package on CRAN, the version that I claim is better, and then the version where we export some of the work to RCPP. We figure out what the bottleneck is, we export that work to compiled code, and now we're going to run this benchmark. So here's what we see. This is the relative performance breakdown of all of these different elements. So for 100 by 100 matrix, the cosine function was the original one. Cosine loop was the one that I'm claiming is better. Relative to cosine, we did much better. But of course, notice that the RCPP version is the victor every time. As the data size grows, the effect, this one is still just kind of crummy. It even gets worse, and then there's a little variability. But here, pretty steadily, is getting better. It would basically never reach the performance of this. It's probably leveling out right about there, actually. The reason why probably has to do with cache effects, where we can sort of avoid some cache misses in compiled code, where once we start getting so much data not fitting in cache as well anymore, the performance degrades. Probably, I actually didn't check. I probably should have, but that's my guess. So a couple of things to point out here, right? You can't just benchmark on a teensy tiny problem and say, well, I'm faster, I win, right? It's 44 times faster. Well, it is for this data size, but maybe that data size isn't relevant to us. Maybe this one is. It's still a lot faster, but you need to understand your inputs. And if I wanted, I could probably even aggressively optimize for that case if I know that that's the one I really care about, and make that number even higher. Basically make the runtime for this one even lower. That may be possible. It may also be a lot of work. The point is, performance benchmark comparisons, you probably don't want to just throw a very small problem at it if it's a really important function to you. You want to understand how it behaves as data sizes change, especially if it's meant to be a very general kind of function. You need to understand how it's operating. And in fact, it may even be different if we make these more tall and skinny, or more short and wide. That may even change the performance profile non-trivially. So just something to point out. What if you add the bytecode compiler? Again, we see these do better, still not very good. The C++ version really is the best for the reasons I've outlined several times. So again, the bytecode compiler helps, not a lot. The runtime for this one basically didn't change when you bytecode compile it. That's pretty, that I would expect that. Quick summary. As we've noted, bad R code often looks like good C and C++ code. Compiled code can be much faster than R code, because I actually heard somebody one time being like, it's only 16 times faster. 16 times faster is really good, right? That's great, because if it takes a day to complete, right, would you rather have it wait a day or a week, or have it complete 16 times faster, and or here 25 times faster? Some problems, again, I've seen several thousand times the performance improvement on the actual data of interest. So it's really useful. It's really easy. But life is complicated, right? The world is not as nice as we hope it would be sometime, or as I hope it would be. So you need to think about these kinds of issues. Hopefully that's reasonably clear. Vectorized code is better than loops, but worse than tailored compiled code. We're basically inventing our own vectorization when we go to compiled code, right? So, exercises. You have a lot of RCPP exercises. They all have solutions, so if you're newer to C++ than you are to R, Hopefully you'll find the explanations and demonstrations in the solutions useful. If you're interested in the use of OpenMP, you can look at, I think it's the last exercise in section 4. You can look at that, and it's RCPP with OpenMP. The performance may not be any better because it was some silly problem, but you can look at how you could do it. So let's take 15 minutes, take a look at those exercises. Then we'll have the final discussion about parallelism. We'll talk about the parallel package, for each package, some stuff with distributed programming in R, and then we'll be done. So take a look. Well, are there any questions? Okay, so hopefully I didn't scare you away from RCPP. It really is great, and it's just, everything's complicated. Everything's weird, right? You have to always think about all these weird contingencies. So hopefully that's good. Take a look at the exercises, and then we'll finish up with parallelism.